everyone. Welcome into lecture number 4 on linear algebra. This lecture is going to be on matrix arithmetic and matrix algebra. So let's first start by remembering what the definition of a matrix is. So I'll write it this way. An m by n matrix is a collection of m times n real numbers. It could be real numbers or complex numbers. Today we're just going to deal with real numbers, but we could extend this to complex numbers. So I'll just write numbers here. But today we'll work with real numbers. These are going to be arranged in an array with m rows and n columns. So our matrices are usually going to be labeled by capital letters or called by capital letters. So I'll just label this matrix A here, this kind of general matrix that we're going to use to help us identify some definitions. The matrices, so the entries in the matrix are going to be arranged in, like I said, m rows and n columns. So they're going to be labeled by their row first and then their column. So the entries will be A11, A12, A13, all the way up to A1n in the first row. Okay, so there are n entries in the first row. Then we go to the next row, and the entries are A21, A22, A23, all the way over to A2n. And this continues down through the mth row. So the last row of this matrix will be AM1, AM2, AM3, through AMN. All right, and again, all of these A's are real numbers. And so one way that we can refer to this matrix is by, we almost always use parentheses to kind of wrap the matrix, the array, as a matrix. So, rounded parenthesis brackets. You'll see sometimes kind of straight brackets, but not just straight lines. So straight lines mean something else on the outsides of our matrix, and we'll talk about what they mean later on in this lecture series. But if we want to refer to the matrix, sometimes we can write it by like its components as Aij with our parentheses here like this. So this notation refers to the entire matrix made up of all the entries lowercase a sub ij. If we just write a sub ij, this refers, without those parentheses, okay, this refers to the real number entry in the ith row and jth column, okay, of Aij with parentheses. So when you put the parentheses, it means you're talking about the entire matrix. Now there are some other things that we'd like to talk about here. Our matrix in general, so I've kind of talked about it, but let me write it down explicitly. So we have m rows in our matrix, and we have n columns. And so we could label this matrix as an m by n matrix. So the space of all m by n matrices, in this case, right, the space of all m by n matrices will denote by a boldface r, real number r, and then m by n up in the superscript. And it's got to have the time symbol, so m by n. So that's how you know that you're referring to an array, a matrix in the space r, m by n. So this is all the m by n matrices, so m rows, n columns with real number entries in each entry. Okay, real numbers in each entry. So this is how we refer to the whole space. Now, matrices that are made up of either only one column or one row, those are sometimes called vectors. So matrices made up of only one row. So for example, for this row, I'll call this one A with a hat. So for our row vectors, we're going to put a hat with like an arrow like this. And so this will be A1, A2, A3 to A sub n. And those made up of only one column So notice these are two different cases, right? One row means that you could have many entries, but they're all aligned in a row. One column is going to mean, so in this case, we'll just write A with a hat like this. One column is going to mean that the entries are lined up. Again, there could be more than one entry, in this case M entries, but they're all aligned vertically like this. All right, so these are both called vectors. All right, and so the spaces of these vectors look like, so the row vectors have one row and you know, however many entries, but this one I put n entries, so the row vectors are going to be a space that looks like R1 by n. All right, so this is the same as Rn in some sense, but because we want to think of this as a matrix, we're going to write it as R1 by n. So these are 1 by n matrices, and the column vectors are the opposite, right? These have m rows, the way I wrote this, but only one column. So the column vectors will be Rm by 1. Where again, m and n are just, you know, placeholders here. They could be any real number, including 1. No, sorry, any integer, including 1. Okay, so these are our vectors. Now, what we will frequently do is we can break up our matrices, our m by n matrices, and think of them as arrays of arrays in some sense. All right, so if we go back to this uppercase A here, we could think of this two different ways, and I'm going to highlight this two different ways. All right, one way that we could think of this is we could think of this as the row vector whose entries are the column vectors. Okay, so we're going to represent the column vectors with just this straight hat here, and notice these go from 1 to n, right? So for a matrix A, again, we're just kind of gathering some notation here. But for a matrix A that's in Rm by n, the columns of A are labeled, we'll say it this way, they're labeled as A1, A2, all the way up to AN, all right? And we can write then that A is the row vector whose entries are its column vectors. So it's getting a little crazy here, right? But we can do this, and we will want to do this. We'll see moving forward. But so A itself can be just rewritten as a row vector whose entries are its column vectors. And so we can think of A as a horizontal array like this. All right. If we can do that, then we can also take the other perspective, right? And that is that we can think of the columns, the rows of A as the vectors, and we can think of A as a column of its row vectors as well, right? So that's another option. So let me highlight this by the color that we just used. All right. And then say, similarly, we know that the rows of A, capital A, can be denoted by, or can be labeled by A with a hat, 1, A, 2 with an arrow, right? So arrow means row in this case, and then A, M. So there's M rows now. And then we can build A by stacking up these rows into a vertical column vector, right? And so this is something that we may find useful. So in this case, A will be equal to the column vector whose entries are its row vectors. And so notice there are M row vectors, there are N column vectors. So each of these row vectors each of these column vectors up here, so just with the straight hat, so A hat with a, so by the way, the column label is the second label, right? And I used AIJ as the label here. So the second label, so this will be A, let me write this in a little bit more detail, sorry. So let me highlight this first, and then I'll write a little bit more detail. So there's another way to write the matrix, right? So here's our more detail. in a little bit more detail, the columns of A, right? So if I wrote A, J like this would correspond to the column vector A, 1J, A, 2J, all the way through A, MJ. All right, so the idea is that it picks out all of the entries whose second component in the index is J, and this obviously lives in R, M by 1, right? For our matrix that's M by N, M rows, N columns, and the rows of A, these ones are A with a arrow hat, I, and these correspond to all the entries that look like AI1, AI2, AI3, right, all the way through AIN. And so this obviously lives in R1 by N, all right, for each of these. And so if you put these all together in the following fashion, then you can build the whole matrix, or you can take the matrix and you can write it in these different ways to try to take advantage of certain properties that you want to use for these matrices. All right, so that's just some notation and some conventions that we're going to set on how we're going to name these matrices, how we're going to refer to them, how we're going to refer to the rows versus the columns notation-wise. All right, and so now what we would like to do is define some operations on these, so arithmetic operations on the spaces of matrices. And we're going to have to be very careful about the sizes of these matrices and how those compare with each other before we try to do any arithmetic with them. All right, so the first thing that we'll do here is just give a definition. But two matrices, let's call them A and B, that both live in the same dimensional space, so are M by N. So these are the same size matrices. These are said to be equal if and only if, there's only one way. So I call these matrices A and B, right? So if and only if their entries A, IJ are equal to the entries B, IJ, that one's an I, for all I and J. All right, so in other words, if every single entry is the same, that's the only way that the matrices can be equal. All right. Now, what we'd like to do then is define some operations on these. And again, we're using real numbers for the sake of this lecture, and we can expand this to complex numbers later. But the operations that we're going to want to use are going to be scalar multiplication. This shouldn't be a surprise, right? Scalar multiplication, and then what we're going to call matrix addition. But you'll see that these form a vector space, so it's going to be vector addition of matrices. But anyway, scalar multiplication. So here's how it's going to work. If we let alpha be any real number, and A be a matrix of any size, call it our M by N, right? Then here's what we need to define, right? So alpha times A is another matrix in our M by N. So you multiply a scalar times a matrix, you get a matrix, and it's given, well, let me say it this way, whose entries are given by, because this is the key, right? If we know how the entries behave, then we know how the matrix behaves. So whose entries are given by, so this is the matrix, right? They're given by alpha Aij. All right? So you just multiply, in other words, you just multiply the alpha component by component. Okay? So this is another way to say this. This is component wise scalar multiplication. Okay, so we'll do an example in a minute, but let's first define what we mean by addition then. We'll call it matrix addition, and then we'll gather all this together in a second. But matrix addition. So this one, for this we want to add two matrices, so that now we have to make sure that they are in the same dimensional space. All right, so they have the same number of rows and the same number of columns. So for this one, we're going to let A and B both be matrices in R m by n, so they have the same number of rows and the same number of columns. All right. The sum matrix, which we'll call C, equal to A plus B, all right, is the matrix, again, in the same space. So it's going to be closed. This operation is going to be closed, but it's the matrix in R m by n whose entries are given by the following formula. So we need to know the entries Cij, right, for this matrix C, and they, it turns out, are going to be the sums of the entries Aij plus Bij. All right, so we just add, again, component by component. So this is component-wise addition for our matrices. So this is just the same as the vector addition that you learned in Calculus 2 for row vectors or column vectors, right? Probably in Calculus 2 you dealt with row vectors, and you learned how to add those component by component or multiply them by a scalar component-wise, right? And these are the same definitions, but they're extended to m by n matrices. All right, so very quickly, let's look at some examples, and then we'll move on to something that we cannot do with general vector spaces, but something special to matrices. But first, let's look at these examples. So let's say that we have a couple matrices. So 1, 2, 3, 4, 5, 6. I'm not going to get clever with this because I just want to make sure that we understand how this works. All right. So let's say we have this matrix, and then B, I'll just count down 9, 8, 7, 6, 5, 4. All right. And then let's just say alpha is equal to 2, for example. Then the matrix 2 times A, right, is defined to be the number 2 times this matrix, 1, 2, 3, 4, 5, 6. And this just goes component by component, right? So we multiply every single component by this scalar 2. And we end up with 2, 4, 6, 8, 10, 12, right? And so that's it. That's how scalar, it's that simple, right? That's how scalar multiplication works. And then the matrix addition is not any crazier. So A plus B is just going to be component by component addition of these matrices. So we're going to add these together. Component by component. So these each have 2 rows and 3 columns. 2 rows and 3 columns. And in your mind, you imagine you could pick this one up. Suppose you could pick this one up and just kind of plop it on top of the other one and add all the entries that land on top of each other, right? So that's all we're doing. And when we do this, we end up with 10, 10, 10, 10, 10, 10, right? So all these sum 1 plus 9, 2 plus 8, 3 plus 7, 4 plus 6, 5 plus 5. That's all, they all add up to 10, right? So that's because of how I chose these matrices. In general, these will always be different entries that depend on both of the entries that in the matrices that you started with, right? Okay, before we get to the next item, what if we try to do something like B minus A? Can we do this if we have these two properties? And the answer is yes, right? So how do we interpret B minus A? Well, we consider this as B plus -1 times A, right? And so in terms of our matrices, it works exactly as you would expect, though, component-wise subtraction, right? Component-wise subtraction, but this is going to be 9, 8, 7, 6, 5, 4, matrix B. And then if I do it by the definition that I've done here, it's plus -1 times this, right? So plus, and then -1, -2, -3, -4, -5, -6. And after this subtraction, what are we going to get? 8, 6, 4, and then 2, 0, -2, right? So we can subtract matrices component by component as well. We don't need to define that because we can build our subtraction out of the two operations that we do have defined. All right. The next thing that we'd like to talk about is matrix multiplication. So by the way, at this point, you have everything that you need. So I'm just going to write this here as a little recommended exercise. But at this point, you can verify that R m by n, so the space of all m by n matrices with these operations if you just go through and work with these operations, that this is a forms of vector space. So each set of matrices, m by n matrices, forms its own vector space over the real numbers, right? So I'm going to leave that as a recommended exercise, but you will want to check that, and we will use that fact to our advantage, that they form a vector space, as we move throughout the semester. All right. But let's now go to something that is not encompassed in this vector space, the vector space definition. So remember, in a vector space, we always have these operations of scalar multiplication and what's called vector addition. In this case, we'll call it matrix addition, but addition, right? Addition of the elements. But what we cannot do in a vector space is multiply two vectors together, right? And it turns out that the space of matrices has more structure because we can multiply them together, except when I said that the space of matrices, I'm not talking about m by n matrices. I'm talking about all matrices together. So why don't we just kind of leave the idea of the vector space in the past and just go on to this next idea of matrix multiplication now. And so I'm going to build this up by first thinking of a simple case. Simple is a relative word here, but a special case, let's call it. So case 1, let's say this. Let's suppose that we have a row vector and a column vector. So let's suppose we have, let's call it A with a hat here, and R, it's a row vector, so 1 by n, and we'll call this one B in R n by 1. So the key here is that they have the same length in the sense of the same number of entries, but one of them is arranged as a row and the other one is arranged as a column, okay? So in other words, our A can be written like this: A1, A2, all the way up to AN, and again they have the same length. So our B is going to be arranged vertically, but it's going to have the same number of entries. So B1, B2 down to Bn. And we want to multiply these two matrices together, okay? So we want to multiply these together. Well, we can do it, right? So the product A times B is the real number defined to be. So again, A times B. It's equal to the real number that we're going to get is going to be the sum of the component-wise products. So A1 times B1 plus A2 times B2 all the way up through AN times BN. So we just match these up. First component of the row vector times first component of the column vector. First component of the component of the row times second of the column, all the way up through the last. All right, and it's very important that it's column first and then row. It's not defined any other way. So this order matters here, okay? But this is defined to be A1, B1 plus A2, B2 all the way up through AN, BN. And this can be written in sigma notation as the sum, I goes from 1 to n, of AI, BI. Okay? So this is how we define the multiplication of a row vector times a column vector. By the way, this is similar to the way that the dot product is defined in calculus, right? Component by component, and then add them all up and get a number back. So this should remind you of the dot product of calculus 2. All right, so we know how to multiply together two vectors in this very special scenario now, right? So it's a vector in R1 by n, so a row vector with n entries, times a column vector in our n by 1. So again, same number of entries, but arranged in a column. And together they give us back a number, right, which we can think of as a matrix, if we wish, in our 1 by 1, a 1 row, 1 column, right? So essentially what's happened here is we've had to make sure that the number of columns of the first one matches the number of rows of the second one, and then those two numbers collapse with each other, and we just got this number back. It's a very simple scenario, right? We just have to make sure they're the same on this one, and then we can do this, right? But we want to extend this now to a more general case where we have matrices, right? So for this one, let's let A, what we're going to do is we're going to keep this letter N the same, okay? So let's let A be a matrix in our M by N, and B be a matrix in our N by R. So again, notice that we have kept the number of columns of A equal to the number of rows of B, all right? All right, so at this point, let's write down the definition of how we're going to multiply these together. So the product, which again I'll call C, just so it has a different letter, C equals A times B. In this case, it's going to be a matrix, but it's not going to be in the same space as either one of the matrices that we started with, all right? So C equals AB is the matrix in the space R. It's going to be, so essentially what's going to happen is these inner dimensions, the ends are going to cancel, and we're going to be left with a matrix in R, M by R, all right? So it's going to have the same number of rows as the first and the same number of columns as the second. And the key here is how we define the entries, right? So whose entries are given by the following. So again, we need to know Cij, right? So Cij, the ijth entry of the matrix C, is going to be the ith row of A. So the ith row of A times the bth j, the bth column of, the jth column of B. The jth column of B. So A times B. All right? And so this entry then could be written in this form, right? So this could be written in sigma notation if we are careful there. So we can write it out. So this is going to be this sum. We've already used I and J, right? So let's use K. So K will have to go from 1 to N. That's the common dimension here. And then in the rows, then this is going to be A, I, K times B, K, J. And we just multiply those out. So there's a couple different definitions there, but let's look at functionally how this is going to work, all right? So this is, again, going to give us, by the way, these entries are now, the rows here are 1 by N, and the columns of this are N by 1, right? And so these work out exactly. It's just an extension of what we did before. We just have to do it for every combination of row of A and column of B. All right, so let's do an example and see how this works. Again, we'll use our simple matrices that we defined before, except I'm going to change one of them. But let's start with A the same way we had it before. 1, 2, 3, 4, 5, 6. All right, and then let's say B is the matrix 1, 2, 3, 4, 5, 6. And we want to multiply these together. This one, by the way, is a 2 by 3, 2 rows, 3 columns. This one is a 3 by 2, 3 by 2. There's no reason that the outside numbers have to be the same, right? But the inside ones do. So if I'm going to do A times B, then these are going to collapse and I should get a 2 by 2 matrix back, right? So let's see how this works. So A times B, I'm just going to write these next to each other. All right. I'm even writing these in rows there and columns here. And so then I'm going to create the new matrix, right? So the product here is going to be the matrix whose first entry, the 1, 1 entry, right? The 1, 1 entry is going to be the first row times the first column. In terms of the same way that we defined our multiplication of these rows times columns before. So it's going to be 1 plus 6 plus 15, right? Okay, so just 1 times 1, 2 times 3, 3 times 5. Now, the first row, second entry is going to be the first row of A times the second row of B. Sorry, second column of B. So this 1, 2 entry is the first row of A, second column of B. Same deal, we multiply these together. So 2, and then we add them up, right? So 2 plus 8 plus 18. So that's going to be exactly how we compute that entry, and that's a number. So that all goes in just one slot, right? All right, so then we go to the second row, first column, right? Like this. And this one's going to be, what, 4 plus 15 plus 30. And that's the result of second row, first column. Second row, first column. That's where it ends up. So it's all exactly the same. Now, next one, second row, second column. That's going to go here, right? It's going to go here. And then when we multiply this out, this one's going to be 8 plus 20 plus 36. All right. So the end result is we have to actually add all these up, right? So this one's going to be 22. This entry is going to be, what, 28. This one's going to be 49. And this one's going to be, what, 56, 64, right? Okay, and so there's the product. And so this is a 2 by 2. Again, we started with 2 by 3. We multiplied it by 3 by 2. The inner dimensions cancel. We got a 2 by 2. Are we allowed to do b times a? Right, so we have to always make sure that the dimensions match up, and it's not always going to be possible for us to switch the order of these. In this case, we can, right, because we got b is going to be a 3 by 2, and a is a 2 by 3. All right, so if we switch the order, then look what we get. We get 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4, 5, 6. This time our answer, though, will be a 3 by 3. A 3 by 3. So we go first row, first column. That goes in the 1, 1 position. First row, first column. I'm just going to work this out. That's 9. First row, second column. 2 plus 10. That's 12. First row, third column. First row, third column. 3 plus 12. 15. Then we move to the second row. First column, 3 plus 16, that's 19. Second row, second column, 6 and 20. Second row, third column, 9 plus 24. All right, and then we just keep going here. So I guess we should finish, right? But third row, first column, so that's 5 plus 24, 29. This is then third row, second column is 10 plus 30, so that's 40. And then finally, third row, third column, 15 plus 36. So 15 plus 36 is 49. All right, so notice, though, that this is a 3 by 3. So very important here. AB does not equal BA. And not only are they not equal, but they're not even in the same space, right? This one lives in R2 by 2. This one lives in R3 by 3. So, and sometimes it's not even possible to multiply together two matrices because their inner dimensions have to match up, right? So for this example that I've given, they worked both ways, but they gave different dimensional answers, right? So it's very important to be very careful as you work through this. All right, so let's return next to the idea of systems of equations, and I'm going to write down a system for us. Very similar to what we studied in the last lecture. So this will be item number 4. Systems of equations revisited. All right, so remember that we have systems of m equations with n unknowns. They look something like this, right? So they look like alpha 1, 1, x1. Very similar naming convention, right? Plus alpha 1, 2, x2, all the way up through alpha, this would be 1n, xn equals b1. And then we went to alpha 2, 1, x1, plus alpha 2, 2, x2, etc. Alpha through alpha 2n, xn equals b2. And this continued until we got through alpha m1, x1, plus alpha m2, x2, all the way up through alpha mn, xn equals b sub m. Right, and this is all forms what we call a system of equations. Then we can kind of wrap this thing up. We talked about the coefficient matrix, right? The coefficient matrix we use to make the augmented matrix, but the coefficient matrix is the matrix that we use to just collect all of these coefficients together, right? So we can just define this thing as A equals, so this is going to be an m by n matrix, and its entries are going to look exactly like what we have just been talking about, right? Alpha 1, 2, alpha 2, 2, alpha 1n, alpha 2n, all the way down to alpha mn, m2. All right, so there's our coefficient matrix, and this is in R m by n. We can also, though, collect the unknowns, right? So the unknowns, if we look at this, the unknowns are, so x1, x2, all the way up through xn, right? So these things are all the same the way they're arranged here, but we can collect these unknowns into a vertical vector, which we can call, say, x bar, and this one will arrange as x1, x2, all the way through xn. There's n unknowns, right? And so this one lives in R, this one lives in our n by 1, right? It has n rows in one column, so our n by 1. And then we can do the same thing with the right-hand side here, right? Our answers, usually what we think of as our answers on the right-hand side. And so we can arrange these as, again, a vertical vector of b's. This time we go b1, b2, through b sub m. So this is a vector in R m by 1. All right, and look at this. The system now can be represented by a matrix multiplication problem. So the system can be represented by, it's equivalent to this actually, right? But it can be represented by this equation. So matrix, coefficient matrix A, that's an m by n, times vertical vector of unknowns x, that's n by 1, right? Multiply those together. The inner dimensions do match up, right? And with n, they do match up, and they give back a vector in Rm by 1, vertical vector, which has to be equal to b, right? Okay, so this is great. So now we can just write our system of equations as a simple matrix equation like this. Now you have to know all the different parts of it for this to be useful, right? But let's take a little bit deeper look at this idea. So we can arrange, again, as we've talked about, we can write down our coefficient matrix as a row vector of its column vectors, right? So we can write this as a row vector of its column vectors. And if we were to do that, and we were to collapse all of these columns into just a single entry, then this would become a 1 by n, right? Where the 1 happens to be vertical vectors. But let me write it out, and then we can see. So we can write A as the columns, right, a row of its column vectors. So this could be, let's call them A, lowercase a. So column A1, column A2, all the way through column A sub n, all right? And then if we multiplied that by x with this in this form, let's see what would happen, right? So these are real number entries. These are column vectors. So in this case, then, A times x is equal to A1, A2 through AN times x1, x2 through xn. Again, these are real numbers. These are column vectors, but you can multiply a column vector by a real number, and usually we just switch the order of it, right? But you multiply this through, you're going to get x1 times column A1 plus x2 times column A2 all the way through xn times column A sub n. And if you add together the sum of column vectors, right, multiplied by constants at each step, then you're going to get a column vector, and this is going to live, these all live in R m by 1. And so the question can be reframed now, right? So by the way, the columns of A are known. These are known columns of A. You're given the coefficients, right? The unknowns are the x's. And we can reframe our entire question as, can we find numbers x1 through xn such that when we multiply and add together these columns of A, that we can make the vector B? Well, that sounds a lot like a linear combination, right? And it turns out it is. So now we can frame our entire question on, does the system of linear equations have a solution? We can frame it as a linear combination problem. right? And remember that if we can write B as a linear combination of the columns of A, then we would say that B is in the span of the column space, right? So it's in the span of the columns, I should say, the span of the columns. And so that's how we can reframe this, right? So these unknown constants are the coefficients that you're looking for that will make the columns of A as a linear combination add up to this vector B. So that's a lot of different ways to say the same thing. They're all saying the same thing, right? So I'm going to write this as a theorem now. But it's very straightforward. So I'm going to write it in symbols, and I'm not even going to write that many words, all right? But let me say this. So the matrix equation, which corresponds to the system of equations, but the matrix equation A times x equals B, where x is the unknown vector and A's coefficient matrix, B is the known right-hand sides, right? This is consistent. Remember, that means there's at least one solution if and only if the vector B is in the span of the columns of A. All right, so that is another way to say that. That is B can be written as a linear combination of the columns of A. Okay. So you can call that the consistency theorem. Remember, consistency refers to whether or not the system of equations has a solution, has at least one solution. So the system is consistent if it has at least one solution. It's inconsistent if it has none. So before we move to the next step here, probably it would be useful to have some notation for the space, the columns of A. So let's write this down. We'll use this, like I said earlier in this lecture, we'll use this later in the course extensively. So we might as well define it now. But if A is a matrix in R M by N, then the column space of A, we can write as col A like this. This is equal to the span of the columns, right? So the columns are A1, A2 through AN. All right, and any spanning set is a subspace, right? We've already proved this. So this is a subspace of R M by 1, which is kind of like Rm. So this symbol here means it means something that we'll make more rigorous later, but it's, it's basically Rm. So the column space of A is a subspace of Rm. All right. Similarly, the row space of A, this is going to be the span of the rows. So that's A1, A2 with these arrows, right? Arrow means row here, just so because it's a different notation. So AM, and this is a subspace of R1 by N, which is again similar to Rn in this loose notation. But the idea is these spaces are indeed important, and we've talked about spanning sets, etc., so we can define these now. The column space of A and the row space of A. Okay, now let's move on to some matrix algebra. I'm not going to prove everything that is, every single property. We've hit the major ones, but there are some more operations that we want to talk about. These are unary operations, so they take one matrix and they return one other matrix. So the first one that we want to talk about, the first operation, is called the transpose. Okay, so let me write it this way. Again, let's start with, let's let A equals Aij this way, okay? Suppose this is a matrix in our M by N. So again, it has M rows and N columns. Then the transpose of A, so the transpose of A, which is denoted by, there's a couple different ways here, a T with a capital T, a T with a lowercase t, or even sometimes T up here on the left, A, as a transpose, right? And in some coding languages like MATLAB, it's just prime. I'm going to actually erase this one because I do not want the prime here, okay? So we're going to use some flavor of T. Either of these two is fine. We're usually not going to put it on the left, okay? But it's either A upper T capital T or A upper T lowercase t. Those will both mean transpose, so they do not mean different things. But this is the matrix in our n by m, and it's denoted by, like I just said, A upper T. Here, let me say it this way then. So we already said I was denoted, but we need to know what its entries are, right? So it's in the space, the opposite space, our n by m, and its entries are given by the following. So because the notation is so weird here, I'm going to write it like this. A upper T I j, this is going to be lowercase a j I. Okay? So the idea here is that we're going to swap the rows and columns. Just literally swap them in order. So swap rows and columns. All right, so here's an example. Let's say A is a 2 by 4 matrix. Let's say 1, 3, 5, 7, 2, 4, 6, 8. So this is in our 2 by 4. It has 2 rows and 4 columns. Its transpose, you can always take the transpose. Its transpose is going to be the matrix whose first column is the same as this first row. So it's going to, the first column will be 1, 3, 5, 7. And the second column will be the second row, right? So 2, 4, 6, 8 will become a column, the second column of A transpose. And it's that simple, right? So you just kind of flip this thing and swap the rows with the columns. That's called the transpose. All right, well, here are some other definitions, but a matrix is said to be symmetric. So symmetric if and only if it's equal to its own transpose. All right, so think about this. If the matrix is going to be equal to its own transpose, then what kind of a space must it live in? So it's going to have to be a must live in a space where the same number of rows and columns, if you're going to be able to take the transpose and end up with the same entry back, right? Not only that, but if it's going to equal its own transpose, then we have to have this relationship, right? That Aij has to equal Aji for all I not equal to j. So as long as they're, because if it's I, then they're already equal, right? So I mean, you could say for all ij, but for this has to work though, especially for what we call the elements that are on the non-diagonal. So let's show what we mean here. Let's do this in 3 by 3. So we'll have A11, A12, A13, A21, A22, A23, A31, A32, A33. We take the transpose, and it's going to reverse the order of the way we numbered this, right? So our first column is actually going to be this first row. So our first column is going to be A11, A12, A13. Our second column is going to be the second row, A21, A22, A23. And then similarly, A31, A32, A33 is the third column. And now we match these up, right? So notice, first of all, that these three did not change, right? They didn't change. So those three can be whatever they want to be. They didn't move in this process. They didn't move. All right? But A12 moved to here, right? And if these are going to be equal, then look at A12 and A21 have to be the same. Similarly, A31 moved to up here. But if these are going to be equal, then that's got to be the same as A1, 3. And so we see this relationship now, right? We can kind of see the relationship. The symmetry is going to be symmetry, if you think of it geometrically, as if we were folding along this diagonal, which I've highlighted as blue. Okay? So here's an example of a symmetric matrix. This can be, I'm just going to write down some numbers, right? 1, 2, 3, and then I'm going to do 4, 5 like this. If this is 2, this has to be 2 for symmetry reasons. If this is 3, this has to be 3 for symmetry reasons, right? If this is 6, this has to be 6 for symmetry reasons. All right, so 1, 4, 5. The diagonal can be anything, but everything else has to be symmetric in this sense that now this matrix will equal its own transpose. Okay, there's another definition here. So a matrix is said to be skew symmetric, and I won't work this whole one out. Not in the same detail that we just did this one, but a matrix is skew symmetric if the following is true. So if and only if A is equal to the negative of A transpose. Or you could say if A transpose is equal to negative A. All right, or minus A. All right. So for this one, in terms of the elements, right, this means that Aij has to equal minus Aji for all Ij. All right, and again, if I and j are equal, this gives us some criteria, at least on the diagonal. So just think about this, right? So thus, Aii has to equal minus Aii, right? So what does this tell us? The diagonal entries must be 0 for a skew symmetric matrix. So here's an example. Again, I won't go through all the details, but here's an example. A is equal to 0, 0, 0. That must be true along the diagonal. And then if I do 1, 2, 3, then over here we have to have negative 1, negative 2, negative 3. Take the transpose, you get the opposite sign. Okay, so pretty simple. All right, we continue moving on now. The next item, we'll call this item 6. There are a whole bunch of algebraic rules. They turn out to be all of the rules that make this a vector space. They make the space of matrices a vector space, and then a couple of extra related to matrix multiplication. Okay, so matrix algebra rules, I'm going to write these all out. And then I'll let you guys verify them as exercises. So it's very important that these all get verified. But they all do hold, and the verification is pretty straightforward. But here's the deal. First of all, we need to make sure that so we're going to need 3 matrices to list these all out. So let's let A, B, and C be matrices of appropriate dimensions. So you're going to have to decide what appropriate dimensions means based on whether the property is of addition or multiplication or what, right? So of appropriate dimensions, and we're going to need 2 scalars here, so alpha and beta be real scalars. Again, all of this works for complex matrices, everything we've talked about so far. Okay, here are the properties, I should say. So A plus B is equal to B plus A, so matrix addition is commutative. Number 2, A plus B plus C is equal to A plus B plus C. Again, you should verify these, but this says that matrix addition is associative. So far, these are required to make it a vector space, right? The space of matrices of dimension m by n. The next couple are not going to be related to those, though. So these are going to be related to matrix multiplication. So this one says A times B times C is equal to A times B times C. So matrix multiplication is associative. Again, you have to make sure that the dimensions match up properly for this, right? So they have to be the correct dimension there. Similarly, matrix multiplication distributes over matrix addition. So A times B plus C is equal to A times B plus A times C. It's very important to make sure that this is that the multiplication is happening on the correct side, right? So this is left multiplication, and it's got to be left multiplication on both sides here, because as we will write here, let's just note it right now before we forget, right? A times B is not equal to B times A for matrices. Matrix multiplication does not commute, right? Does not commute. Okay, but this is a distributive property, and kind of on the same note of what I was just saying, the distributive property does work on the other side as long as we keep everything in the right order. So A times C plus B times C. Keep everything in the right order. All right, so these three are all about matrix multiplication. They're very important. Make sure you check them. Make sure you get the appropriate dimensions for those ones. Those ones are not involved with the any space of matrices being a vector space, though. Let's write a couple more. So these ones are related to scalar multiplication. So alpha times b times a is the same as alpha times beta times a, alpha beta. All right, so scalar multiplication is associative. Property 7, scalar multiplication, that's scalar with scalar, right? But also scalar multiplication is associative with vector multiplication, or sorry, matrix multiplication. So again, this is another one that's not involved with the vector space. But this is the same as alpha A times B, which is the same as A times alpha B. So we can associate the scalar with whichever matrix we want when we do matrix multiplication. And you can work that out. It's pretty straightforward. And then a couple distributive properties. So alpha plus beta times A is alpha A plus beta A. And similarly, alpha times A plus B as matrices, alpha A plus alpha B. All right, so again, so again, these properties should all be verified. So you should verify these. And make sure that when you do so, you check the dimensions and kind of state the dimensions of your matrices that are gonna lead to the successful results, right? Okay. The only other thing here that you'll need if you're going to verify that, again, so I've been talking about this a lot, and I'll stop. But if you want to verify that R m by n is a vector space. Right. The only other thing that you'll need that's not listed here, there's two things, I guess, but one of them is you need the zero matrix, right? So the zero matrix in Rm by n is probably exactly what you expect it to be. So the zero matrix is the matrix whose all of which they're entries, right? The matrix for which all entries are zeros. So this is the additive identity in the space of m by n matrices. And the other one is the inverse, right? So minus A is going to be, and there's a theorem about this that we learned, but we can take this to be our definition of the inverse. It's going to be -1, the scalar -1 times A. And we kind of talked about how you do subtraction a little bit earlier in this lecture. So you'll need these two to verify that this is a vector space. And again, you should do that. Verify that it's a vector space. Okay, so the next thing that we'd like to talk about are powers of matrices, and you can probably guess how this goes as well. Everything kind of goes exactly as you would expect, but we have to write it down. We have to study it, right, to make sure that it truly does work exactly as we expect. But we can take powers of matrices, at least integer powers of matrices. All right, so we can write, so let's say, again, I should be more clear. Let's suppose, we can't do this for any matrix, right? So the only matrices that we can take powers of are matrices that are what we call square matrices. So let's let A be a matrix in the space R n by n. So it has the same number of rows with columns. Then we can define A squared, right, to just equal A times A. And again, this will live in n by n dimensional space, right? Because the number of rows and columns, there's 2 copies of this, the n's cancel, but you're still left with n's on the outside, right? If you think of it kind of systematically like that. But if we can do this, then we can do as many as we want, right? So we could say, and a to the kth power is equal to a times a times a k times for any positive integer k. All right. So, I mean, it's, again, pretty straightforward, but we can do this. So you can multiply a matrix by itself multiple times. Now, we can define a couple different properties of matrices that are related to their square and maybe to higher power. So here are some definitions then. But a matrix is said to be idempotent if and only if a squared is equal to a. All right, so if you square the matrix and you get back itself, it comes back as itself, then that's said to be an idempotent matrix. Similarly, a matrix is said to be nilpotent if and only if a to the kth power, so ak, is equal to the zero matrix for some k. So this z represents the integers, right? So z plus. So if you multiply the matrix by itself a number of times, you know, it could be just 2. A squared equals a zero matrix, or it could even be a to the third power, fourth power, fifth power. If that equals the zero matrix, then your matrix is said to be nilpotent. Okay. For the last one, we need to define another matrix, and this is called the identity matrix. And the identity matrix is the multiplicative identity in the space of square matrices. So the identity matrix of dimension n. So if there's a different identity matrix for every space of square matrices, right? So let me say it this way: the identity matrix in R, n by n, is the matrix denoted by I, and it's got n rows and n columns, right? And so it's got ones on its diagonal and zeros everywhere else. Okay, so in other words, this matrix I, the ijth entry, is equal to 1 if I equals j, and it's equal to 0 if I does not equal j. And it's got to be a square matrix. Okay, so it's called the identity matrix. So for example, in three-dimensional space, sometimes you could call this I3 if you just want to make sure that it's clear what space you're working in. But this I3 is just equal to the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. All right, and again, you don't have to write the 3 there. You can just write I, and everyone will understand what you're talking about. Okay, so we have one last definition in this item, and then we have one more item to go. So a matrix is said to be an involution. So it's either involutive or an involution if a squared is equal to the identity matrix. All right, so if you think of multiplying this by, say, a vector, and then multiplying that vector by the same matrix, you'd get back the original vector. So we'll talk about that as we move forward, but involutive is the property that a squared is equal to I. By the way, it's kind of interesting that the identity matrix itself is involutive, because you can multiply this out. I times anything is equal to itself, it turns out. So a times I is equal to a. So again, we'll make this a recommended exercise, but a times I is equal to a. This is true for all a, and actually R m by n, and the I in this case is in R n by n. But it's certainly Yeah, it's on the right-hand side. Yep, that's right. So it certainly applies to I itself then, right? So I itself is involutive itself. Okay, one more thing that we would like to talk about, and that is the inverse of a matrix. And we'll spend a lot more time on this as we move forward as well. But again, let's let A be a square matrix. So these are the only kind, again, square means the same number of rows and columns. These are the only kind for which this is even possible. All right? So then A has an inverse matrix, B in the same space, so also in Rn by n, if n by n, square space, so also in Rn by n, if and only if A times B is equal to I. Again, in the same space. So if we can find a matrix B for which A times B is equal to the identity matrix, then we say that A and B are inverses of one another. And we can write, in this case, that B, we can denote B by A inverse in this kind of function notation. A inverse, if we wish. All right, so I want to work this out, but first let's give some definitions. So notice the way I wrote this is A has an inverse matrix B if and only if such a thing exists. It's possible that A could not have an inverse. So there are many matrices that do not have inverses. Okay, and so this is where this next definition is headed. So a matrix is said to be singular. So a matrix A in Rn by n is said to be singular if it does not have an inverse. So if there's no inverse, the matrix is singular. And it's said to be non-singular if it does have an inverse. So non-singular means that it does have an inverse. And it's going to be one or the other, right? It either has an inverse or it doesn't. So singular versus non-singular. All right, here's a theorem, and then we'll finish this lecture by working out some examples of how to compute the inverse of a matrix, at least for 2x2 matrices. So here's what the theorem says. If A and B both live in Rn by n, and they are non-singular, then their product matrix, A times B, or B times A, either direction, but AB is also non-singular. All right, and we can even write this. Whoops, the inverse of AB, so if you use this notation, the inverse of AB is equal to B inverse times A inverse. All right, so it switches the order and distributes the inverse in some sense here. Okay, so like I said, let's work out some examples here. Just in 2x2, so let's let A equal this matrix 2, 4, 3, 1. I want to know, first of all, is it singular or non-singular? And if it's non-singular, can we find its inverse? So here's one method for doing this. All right, so one method for working this out is to use the augmented matrix approach that we had developed in the last lecture. So you would just put your 2x2 matrix, your square matrix, on the left-hand side of an augmented matrix, and on the right-hand side you put the identity matrix. All right, and then you perform row operations. So you use row ops to kind of swap the identity matrix to the left. So you're going to get this to be the identity matrix on the left by using row operations, and then whatever's here, if it was possible to do this, then whatever's here on the right hand side now is the inverse. Okay, so whatever's on the right hand side is the inverse. So let's do it. Let's first start by I'm going to write out all my row ops. I'm going to replace row 1 by 1/2 of row 1. So I guess I wrote that wrong, right? But I want to replace row 1 by 1/2 of row 1. All right, and so this will then be 1, 2, 1/2, 0, 3, 1, 0, 1. Then I want to do row 2 replaced by what? Row 2 minus 3, row 1. So this will then be, row 1 is going to stay the same, right? Row 2 is going to be now 0. This 1 minus 3 times 2 is -5. 0 minus 3 over 2. So -3/2, and then 1 minus 0. Then at this point, there's only a couple more steps, right? But replace row 2 by -1/5 of row 2. So get this out and make that a 1. We'll be close, right? So at this point we have 1, 2. 1/2 here, 0. This will be 0, 1. This will become negative. The negative we're going to divide through by -5, right? So this is going to become positive 3/10. And then this is going to become positive 1/5. And then there's only one more step, right? So the last step is to replace row 1 by row 1 minus 2, row 2. So this is now the Gauss-Jordan step, right? We've done Gaussian elimination up to this point. We have one more step to go to the Gauss-Jordan, and then we'll be done. So the last row, by the way, is done. So this 3/10, 1/5 down here, that's all going to stay. Up here, when we subtract, we're still going to have 1. 2 minus 2, that's 0. That's the whole point, right? 1/2 minus 2 times 3/10. So 1/2 minus 6/10 is going to be -1/10, right? And then same thing here. So this is going to be -2/5. -2/5. And so as long as I did that all correctly, this is now our matrix A inverse. So for the given matrix A, we have computed by this row operation method that its inverse is -1/10, -2/5, 3/10, and then 1/5. Okay? And so at this point, you should check and make sure that these two are indeed inverses. Remember how you do that. You multiply A times A inverse, or you can multiply A inverse times A, and both of those should give you back the identity matrix, right? They should both give you back the identity matrix. So let's just check really quick just the first entry. 2 times negative, so these both have a denominator of 10, right? So -2 plus 12, 10 over 10. It's good, right? So I'll let you guys do the rest of them, but check them all, make sure that this really works. But that's how you compute the inverse of a matrix using row operations and augmented matrices. All right. So you can also do this with 3x3, 4x4. It becomes a little bit tedious, right? So later in the semester, we will come up with other ways to determine our matrices. But before we do, the last thing that I'd like to do in this lecture is to just look at an example of a matrix that does not have, so we'll do a 2x2 again, but a matrix that does not have an inverse. So let's say we have A is 1, 4 in the first column, and then let's say -2, -8 in the second column. Okay, so let's try to work this out the same way. Try to find the inverse. All right, so A inverse. This is our question. Can we find a formula, or can we find the matrix that is the inverse of this A? So we'll go through the same steps. We'll set up our augmented matrix, and we will apply row operations, right? So this is already a 1. We just need to get rid of this, right? So we're going to take our row 2, and we're going to replace it by row 2 minus 4 times row 1 to get rid of this. And let's look at what happens here. Our row 1, by the way, is the same. Nothing wrong with that. We're not changing it, right? The second row now, we have 4 minus 4, 0. -8 minus a -8, so that's 0, right? And then we can keep going, but we already, I think, know what's going to happen, right? 0 minus, so this is -4, 1 minus 0 is 1. But look what's happened here, right? So we now have a row of all zeros on the left-hand side. So it's going to be impossible for us to get the identity matrix on the left, right? So this is impossible. So this is a matrix that does not have an inverse then. Once you arrive at this, again, your goal is to get the identity matrix on the left-hand side. If you can't do it, then your given matrix is singular. So this A is singular, does not have an inverse. All right? So that's what it'll look like if you come across a matrix that does not have an inverse and it's singular. You'll end up with, at some point, a row of all zeros, or something else will go wrong that will make it so it's impossible to get the identity matrix on the left-hand side of your augmented matrix. All right, this was a long lecture. Let's leave it here, and I'll see you guys in the next one.